function f of x is equal to 2x squared minus 2x minus 12 over 3x squared minus 12. Obviously, there's some factoring that we can do here, but before we factor, let's determine horizontal asymptote or slant asymptote. So we're comparing degrees. The numerator is degree 2, the denominator is degree 2, so when they are the same, it is y equals the ratio of the leading coefficients. So the number that's with the highest powered exponent. The majority of the time, these are going to be listed in standard form, but be careful. Sometimes they like to throw one in there where they do it in reverse order, meaning maybe the 3x squared's at the end of the denominator. Okay, it doesn't have to be at the beginning to be considered the highest powered exponent. Okay, it's not always what's at the front. Look for the biggest exponent and you use its coefficient. So our horizontal asymptote is y equals 2/3. Let's go ahead and put a horizontal line at y equals 2/3. So do your best estimating there between 0 and 1. You don't want to be right on the 1. Okay, now the rest of this requires that we factor and cancel. So let's do that. The numerator, we need to begin by pulling out a GCF of 2. So when we do that, we're left with x squared minus x minus 6. And in the denominator, we have a GCF of 3, which leaves us with x squared minus 4. Both of those factor further. We've got x minus 3 times x plus 2. And the denominator is the difference of perfect squares, so it's x plus 2 times x minus 2. Very important that you make sure your signs are correct, particularly with like this numerator. Make sure that you've got the 3 as negative and the 2 as positive, and make sure that's the correct scenario, because obviously that makes a difference with this denominator as to what is the whole and what is the vertical asymptote. The one that cancels is the whole, the one that's left is going to be the vertical asymptote. So in this case, the x plus 2 cancels. So I'm going to go ahead, since I marked it out, I'm going to go ahead and write x plus 2 equals 0 beside my whole. And then I'm going to come back up here and I'm going to write the simplified version of my equation. So the simplified version is 2 times x minus 3 over 3 times x minus 2. Okay, let's go back to figuring out our whole. Obviously, if we solve this for x, we're going to get x is equal to negative 2. That's only part of the answer. The whole is a point on your graph, so you have to have the y-coordinate. The y-coordinate comes from taking that x value and plugging it into the simplified equation. So we're plugging in negative 2 in for x in the simplified version of our equation here. So let's see here, we get 2 times negative 5, we get negative 10 in the numerator. We get 3 times negative 4, that's negative 12 in the denominator. So if we simplify that, it simplifies to positive 5 over 6. So our whole, write it as a point. The x-coordinate is negative 2. The y-coordinate is 5 over 6. And then go to your graph, and we need to fill this in. 5 over 6 is bigger than 2/3, because 2/3 is 4/6. So I'm really going to have to squeeze on mine. If I can, here we go. Move my horizontal asymptote down just a little bit and fill in my whole. Hopefully you can, yours isn't quite as crunched as mine is, but the whole would be there at negative 2, 5 over 6. Between the horizontal asymptote and y equals 1. Okay, vertical asymptote, we take what's left in the denominator and set it equal to 0. So we've got 3 is equal to 0, and we have x minus 2 is equal to 0. Now, is 3 equal to 0? No. Okay, so I'm just going to mark that out. But the reason why I write it is because in some cases, that GCF, that 3, it may be a 3x. So if it were a 3x, then that is possible for 3x to equal 0, right? If your x is 0. So I write it there just to be in the habit of not ignoring that term if it were to have a variable in it. This one did not, but it could also produce another vertical asymptote. It is possible to have more than one vertical asymptote. So in this case, we just had the x minus 2 is equal to 0, so that says x equals 2. So, whoops, didn't do that. We have our vertical asymptote at x equals 2. So draw a vertical line at x equals positive 2. Now, the reason why it is a vertical asymptote is because if we plug positive 2 into this function, the numerator is fine. We would get a number, if we plug it, what do we get? 4, 8, 8 minus 4 is 4. We get negative 8 in the numerator if we plug in positive 2, but if we plug positive 2 into the denominator, we get 0. Negative 8 divided by 0 is undefined. So this causes f of x to be undefined. So we will not have any points. There will be no point when x equals 2 that we will be able to produce any y value and have any graph here at x equals 2. That's why we draw that vertical line there. We cannot have a value anywhere on that vertical line because x equals 2 causes the function to be undefined. It has no value. The function has no value at that x value. Okay, our x-intercept. Okay, our x-intercept, we take our simplified numerator and set it equal to 0. Well, it's similar to our denominator. We've got two pieces. We've got 2 and we have x minus 3. Obviously, 2 does not equal 0, but for the same reason that I just explained with the vertical asymptote, I still want to be in the habit of writing that down because what if that were a 2x? If it were 2x, then we would get x equals 0 as an x-intercept. But in this case, we only have 1. And just to re-emphasize the fact that the x-intercept is a point and its y-coordinate is always 0, I'm going to write that as 3, 0, and then I'm going to come over here and plot my point on the x-axis at x equals positive 3. Y-intercept, we can plug 0 into the original function or we can plug it into the simplified version. Typically, it's usually actually easier to go back to the original function because if x is 0, then that doesn't matter, that doesn't matter. The only thing we've got left is the negative 12. The 3x squared is going to be equal to 0, so we're left with the negative 12 in the denominator. Negative 12 divided by negative 12 is positive 1. So when we plug in 0, the result is positive 1. If I plugged it in the simplified version, I'd get the same answer. I get 2 times negative 3 over 3 times negative 2. Guess what? That simplifies to positive 1 as well. So y-intercept 0, 1. And now let's talk about the behavior around the vertical asymptote. So our vertical asymptote is x equals 2. So let's write it this way. Let's say as x approaches 2 from the left. I think we mentioned this a little bit in Math 3, but if not, that's what this notation means. This little negative up here, it's not supposed to be in front of the 2 because our vertical asymptote's at positive 2. That when you make it an exponent, that says you look at 2 from the left. And then we're also going to look at 2 from the right. We put a little plus as an exponent on the 2. That means from the right. So this is left of 2. This is the right of 2. The question is, what are our y values doing? What are our y values doing to the left of 2 and to the right of 2? Now, I'm going to do this two ways. I'm going to consult the calculator, and then I'm also going to do it without the calculator. Let's do it without the calculator first, since I haven't done anything in the calculator yet. The quick and easy kind of cheat way to check this is to pick a number that's close to 2 on its left side. So something like 1.75. Okay, 1.75. If I plug 1.75 into my simplified equation, let's think about, I don't want the exact number. My concern, is it positive or is it negative? Is it positive or is it negative? So 1.75 minus 3, is it positive or negative? 1.75 minus 3 is negative, okay? So my numerator is negative. So I've got a negative over, when I plug 1.75 into the denominator, 1.75 minus 2 is negative, and I'm multiplying it by a positive number, so the result is negative. So a negative divided by a negative is positive. So based on that analysis, my y value, I can confidently say that it is headed towards positive infinity. Because when I pick a number close to 2 on its left side and plug it in, I'm just checking the sign, okay? Because if you remember a little bit about vertical asymptotes from Math 3, one side is, you're always going to infinity. As you get closer and closer to a vertical asymptote, your graph is taking off. It's either going up or it's going down, but it's always going to be approaching an infinity with your vertical asymptotes. So let's do it on the right side. Let's do like 2.25. Okay. You don't want to pick a whole number because sometimes those can get a little tricky. You want to pick something pretty close, or really like 2.1 would have worked. Okay, but it'll still work here. Okay, 2.25 minus 3. 2.25 minus 3 is negative, and negative times positive 2 is a negative. In the denominator, 2.25 minus 2 is positive. And we're multiplying it by positive 3, so the result is positive. A negative divided by a positive is a negative. So these y values are going to negative. Now, that is something that you will 100% have to do in calculus. Without a calculator, you will have to do this analysis, this idea of picking a value close. You're not really worried about what numerically it's equal to, you're just worried about the sign. Is it positive, is it negative? So if calculus is in your future, you need to understand this. Now, if you don't think calculus is in your future, then the calculator does everything you need it to do. Okay. So we obviously need to finish this graph. This is not the graph of the whole rational function. So put the original in your calculator, making sure that you put parentheses around the entire numerator, parentheses around the entire denominator. And just for good practice, I'm also going to plug in my simplified equation because I'm going to show you something about that as well. Okay, so I put in the original, parentheses around the numerator, parentheses around the denominator. I also plugged in the simplified. Same thing here, I need parentheses around the whole numerator, not just the x minus 3, and the whole denominator, not just the x minus 2. So then we can go to the graph, and that agrees with what we've got so far, or seems to. Now, I really don't like graphing these on the graphing calculator because it almost always looks like this heartbeat monitor. Okay, That kind of vertical line there, guess what that is? That's our vertical asymptote. Okay, but that's not really how we want to draw our function. These calculators are limited in their resolution, so they can't graph it very, very precisely like we need it to. So that's why we kind of end up with this kind of looking graph. But we can use that to fill in the detail that we need. We can see that, okay, our function's leveling off right here, which is what it's supposed to do around the horizontal asymptote. It's supposed to level off to that value. It's going to positive infinity on the left side of positive 2. On the right side of positive 2, again, I don't like what this calculator does because it looks like it stops, but it doesn't. It keeps going down. And then over here on the far right side of the graph, it is leveling off to that horizontal asymptote as well. If you really want to, we could have also graphed our horizontal asymptote of 2/3. We could do y equals 2/3 and kind of confirm that that line fits right in there between those two curves. If you had incorrectly, say that you said that for whatever reason, you said that the horizontal asymptote was 0. Okay, if you plug in y equals 0 and you look at your graph, okay, there's our rational function. And then we're waiting. It says that it's done graphing. I didn't see a horizontal line show up right in between those two curves. It's because y equals 0 is the x-axis. That's why we really don't see it here. But that tells you your horizontal asymptote is not correct. Okay, one more thing. Let's look at the table because this is what I wanted. This is why we put in the original and the simplified equation. When we look at the table at x equals positive 2, we have an error in both y1 and in y2. Well, positive 2 was our vertical asymptote. So I already discussed with the original, it gave us -8/0, which is undefined, which is why it gives us an error. But even in the simplified version, 2 is still going to cause us to have a number in the numerator, but 0 in the denominator, so it's still undefined. We can't fix a vertical asymptote. It's still a problem. Now, our whole, on the other hand, if we go over here to x equals -2, we see the error in y1. Okay, if we plug -2 into the original, we get 0/0. But if we plug -2 into the simplified version, we don't get 0/0 anymore. We worked it out to 5/6, but 5/6 as a decimal is 0.83333. Okay, so that is how vertical asymptotes versus wholes show up in the table, and you can kind of use it to confirm your answers there. Okay, obviously that took a long time to develop that, but there were a lot of things that I needed to review from what you already knew about graphing rational functions. This one should go a little bit faster. Look at the next example. -4/x² minus 3x. Horizontal or slant asymptote. Comparing the degree of the numerator to the degree of the denominator. The numerator doesn't have a variable, so it's considered degree 0. The denominator is degree 2, so it's bigger on the bottom. That's JLO. Y equals 0. Y equals 0 is your x-axis. So notice I have a thicker, bolder line here because you've already obviously got a line at y equals 0. You need to make it a little bit more obvious that it is a horizontal asymptote. Do you make sure that you make it a dotted line? Because it's not technically a part of the graph, okay? It's not a part of your graph, which is what a solid line would imply. It's kind of a boundary, okay? It's a guide for your function. So that's why we use a dotted line instead of a solid. All right, If we look at factoring this, the numerator is just a constant, so there's no factoring that we can do there. The denominator does have a GCF of x, so we can pull that out. But obviously, if we didn't factor anything in the numerator, nothing cancels. So this one does not have any holes. You don't have to have a hole. You can have more than one, but you don't have to even have one. Okay, vertical asymptotes at the simplified denominator equal to 0. Here's that case that I was warning you about. We have that GCF of x, so we've got to set that equal to 0, and the x minus 3 equal to 0. So this one has two vertical asymptotes. X equals 0, which is the y-axis. X equals 0 is the y-axis, and then x is equal to 3. So we have two dotted vertical lines on this rational function. Okay, x-intercept, we said the simplified numerator equal to 0. Well, our numerator is -4. -4 does not equal 0. We do not have an x-intercept. You don't have to have an x-intercept. Okay, y-intercept, we plug in 0 for x. Now, if we plug in 0 for x, we get -4 over 0, which is undefined, so we don't have a y-intercept either. The bigger reason why we don't have a y-intercept is because we have a vertical asymptote on the y-axis. You cannot touch or cross a vertical asymptote. So that completely eliminates our y-axis. So no y-intercept. Okay, behavior around the vertical asymptote. We have two of them. So we need to do two analysis here. 0 from the left, 0 from the right. 3 from the left, and 3 from the right. In all these cases, we're wanting to know where are our y values headed. So I really want us to continue to practice with the whole sign analysis thing. So let's do that. 0 from the left, let's use -0.1 for an example. Okay, -0.1. So the numerator is always negative. The numerator is always -4, so we don't have to worry about that. We just need to worry about the denominator. So we've got a negative times -1 minus 3 is going to be negative. So a negative times a negative is a positive. So numerator is always negative. In this case, the denominator is positive. So negative divided by positive is a negative. So that means I don't know a whole lot about my graph, but technically I can go over here and to the left of my vertical asymptote at 0, I can draw part of my function going down to -infinity, because I know that that's what's happening on that side of the vertical asymptote. Okay, 0 from the right. Let's try a positive 0.1. Again, the numerator is always negative. The denominator, 0.1 minus 3 is a negative. So this part is negative. This is whatever x is, which is positive 0.1. So positive times a negative is a negative, and a negative divided by a negative is a positive. So on the right side of 0, our function is going to positive infinity. Okay, 3 from the left. Let's do 2.75. A number to the left of 3, but close to 3, 2.75. So numerator is always negative. Denominator, we've got a positive times a negative. So negative over a negative is positive. So this one is going to positive infinity as well. 3 from the right, 3.1. Numerator is always negative. We've got a positive times positive. 3.1 minus 3 is positive. So negative over positive is a negative. So on the right side of on the right side of positive 3, we are going to negative infinity. Now, we didn't have any x-intercepts, we didn't have any y-intercepts, we didn't have any holes, so we don't have any other points on our graph here. Let's go to the technology and get some more detail, clear out all this stuff, and get some more detail about our graph here. -4 over x squared minus 3x. There's no point, it didn't simplify. Yes, I factored it, but it didn't simplify, so there's no point in typing in the other equation. Okay, and then judging by this, I can see what it's supposed to look like. I don't know about you, I like just a couple of exact points. So how about -1, -1, just to give me a little bit of definite value here to my graph. 1, 2, 2, 2, and we've got a little parabola going on here, so I don't know exactly where it goes, but say it looks something like that, and then 4, -1. That's what this rational function looks like. Okay, one more example. We'll do one with a slant asymptote, and then we will practice later. Okay, example number 3, x cubed minus 9x over 3x squared minus 6x minus 9. The degree of the numerator is exactly 1 degree greater than the denominator, so this is the case where we have a slant asymptote. To find our slant asymptote, we have to use long division. So let's set it up. 3x squared minus 6x minus 9. We're not missing any powers, not missing anything there. X cubed, we are missing x squared, so put a 0x squared there. Minus 9x, we are missing a constant term, so put a plus 0 on the end. Now, quick review of long division. You take the first term and divide it by the first term. So x cubed divided by 3x squared. Now, probably most of the time when you did this in Math 3, that always came out to an even whole number. In this case, it doesn't, right? We've got 1 divided by 3, so that's 1/3. X cubed over x squared is x. So 1/3 x. Line it up over the 9x. Okay, line it up over the degree that it matches. Then we take this 1/3 x and we multiply it by all 3 of the terms of our divisor. Okay, so 1/3 x times 3x squared is x cubed. That's what's supposed to happen. 1/3 x times -6x is -2x squared. And 1/3 x times -9 is -3x. Our next step is to subtract. The easier way to handle it is you just change all the signs and you add. That's the same as subtraction, okay? Changing all your signs and adding. The first one should always cancel. X cubed plus -x cubed, that cancels. 0x squared plus 2x squared is 2x squared. -9x plus 3x is -6x. And you bring down the 0. And then we repeat the process. 2x squared is now our first term. 2x squared divided by 3x squared. So that equals 2/3. Now, here's the good news about using long division to find slant asymptotes. That's all the work that you have to do. Technically, the long division process is not over, but it doesn't matter. This is our slant asymptote right here. Y is equal to 1/3 x plus 2/3. That is the equation of our slant asymptote. Now, obviously, that one's a little tricky to graph. Your y-intercept is 2/3, and then you need to follow a slope of 1/3. Rise 1, run 3. Rise 1, run 3. Okay, try and fit that in there as best you can. Any questions about the long division there? Okay, moving on. Whole, we need to factor. So in the numerator, we have a GCF of x. In the denominator, we have a GCF of 3. Numerator, difference of perfect squares, x plus 3 times x minus 3. Denominator, x minus 3 times x plus 1. So our common factor is the x minus 3. That's going to give us our whole at x equals positive 3. Come up here, write your simplified equation, x times x plus 3 over 3 times x plus 1. Plug the 3 into the simplified equation for x. So we get 18 over 12, those are both divisible by 6, 3 over 2. So 3 over 2 is our whole, and that 3 over 2, 1.5 is going to be just below your slant asymptote.